Boy, it feels good to be back here at college again, teaching mathematics. Welcome back to my YouTube channel. So in this video, I'm going to be showing you every math class that I took in college. And if you didn't know, I was a math major at Rutgers, and I had a serious interest in the math classes that I took. Every time in class, I would just enjoy the lectures, and I would write notes down from my professors. When my professors would write down something, I would enjoy it, and I always loved the math class that I took. So in this video, I'm also going to be showing you every problem that I learned in each class. Alright, so in this first problem here, we're asked to find the limit as x goes to 0 of square root of x squared plus 4 minus 2 over x squared. So let me rewrite this. And the first step I would do is I would multiply by square root of x squared plus 4 plus 2 on the numerator and the denominator. In other words, I'm multiplying by its conjugate. Then from here, we could take the square roots, x squared plus 4. Square roots go away on that. Then the outside and the inside products cancel. And negative 2 times 2 is negative 4. And on the bottom we have x squared times square root of x squared plus 4 plus 2. And we can see that the 4's will cancel. And the x squares will also divide out as well. Let me simplify this. It would be 1 over x squared plus 4 plus 2. Now I could just evaluate the limit by plugging in 0. Square root of 4 is just 2. 1 over 2 plus 2. And it's 1/4. So the answer is 1/4. As the limit as x goes to 0 of square root of x squared plus 4 minus 2 over x squared. And this is an example of a calculus 1 problem that I learned in college. So in this next problem here, we're trying to evaluate the integral of x times sine of x dx. And this is a problem I remembered from my calculus 2 class. And I would use this method called the integration by parts. So let me rewrite this to remember. U dv minus uv minus the integral of v du. U would be x, and dv would be sine of x. Right, since I had u and dv as u as x and dv as sine of x from the top. From here, we're trying to figure out what du is in this. In this case, the derivative of x would be 1, and we're trying to find what v is. In this case, it would be the antiderivative of sine of x, which in this case is negative cosine of x. Now let me rewrite this. Let me simplify from here. And from here, we're trying to figure out what the antiderivative of cosine of x is. Well, in this case, it's just sine of x. let me write this. So this is an example of an integration by parts from my calculus 2. And we see that the integral of x times sine of x dx is equal to negative x cosine of x plus sine of x plus c. Alright, so in this next problem here, we're trying to solve this 3 systems of linear equations using the Gauss-Jordan elimination method. And what I remembered in my linear algebra class is when you're trying to solve this Gauss-Jordan elimination with 3 systems of equations, I would think of it as a matrix. And you have ones on the diagonal, and then you have zeros on the upper triangular matrix, and zeros on the lower part of the triangular matrix, and you have some constant A, B, and C. So we're trying to get it into this form. So let me rewrite this 3 systems of linear equations. So we're trying to get it into this form here. And what I would do first is I would want to get this one over here to be a 0. So turn this 2 into a 0. And what can we do? Well, we can do R2 is equal to R2 minus 2R1. So let me rewrite this. Let's do R2 is equal to R2 minus 2R1. So this would be 1, 1, 1, 5. 0, 1, 3, negative 2, 4, 0, 5, and 2. Now that we have a 0 over here, we also want to have a 0 over here too. So let's try to replace that 4 with a 0. And what can we do there? Well, we can figure out and see that we can do R3 is equal to R3 minus 4R2. That's the way to eliminate it. And get that to be 0. Now we got a 0 over there. And now we want to have a 0 on this side over here. So let's replace that negative 4 to a 0. And what we can do is we can do R3 is equal to R3 plus 4R2. Let me rewrite that again. Now we have a 0 over there. And now we want to have a 1 on this side here. So replace that 13 with a 1. And what we could do is we could do R3 is equal to R3 over 13, or 13 times R3. You write that? Now we want to get a 0 on this row over here. So let's replace that 3 with a 0 by using R2 is equal to R2 minus 3R3. Do that. Now we need to get a 0 on this top matrix right there. And what we can do is we can do R1 is equal to R1 minus R3. Let me write this over here. And finally, we need to get a 0 on over here. What I can do is let's see what I can do. I can do R1 equal to R1 minus R2. That way we get a 0 on the side. And we can see it's now in this form, and we have our constants, A, B, and C. Well, let's just replace it. So let's say x is equal to 3, y is equal to 4, and z is equal to -2. And these are our three systems of linear equations. And if you plug in x, y, and z back into the three systems of original linear equations, you should see that they should all work. Alright, so now in this problem here, we're trying to solve this triple integral problem. We can see we have the integral of 0 to 1, 2 to 3, 1 to 2 of x squared times y times z to the third dx, dy, and dz. And what I like to do first here is I would like to take the integral with respect to each variable. So let's work with the x's first. So the integral of x squared dx would be x to the third over 3. Now let's plug in 2 and 1. So f of 2 would be 2 to the third. So this would be 8 over 3. And let's plug in 1. And subtracting these, we get 7 over 3. Now let's work with the y. Let's see. Integral of y dy. The antiderivative of y is just y squared over 2. Now let's plug in 3 and 2. This will be 9 over 2. And we have 2. Subtract these two, and we get 5 over 2. And now let's take the integral with respect to z now. That is z over 4. And let's state the boundaries of that. And f is 0. 0. Now we can multiply all these. 7, 3 times 5 times 1/4. And this should equal 35 over 24. And this is an example of a triple integral problem that I remembered from my Calculus 3 class. Alright, so in this next problem here, we're trying to solve this second order linear differential equations. So we have y double prime plus 3y prime minus 10y is equal to 0. And I remembered this from my differential equations class. And the first step I would do is I would write y is equal to e to the ax. So what's the derivative of that? Y prime is just a e to the ax. y double prime would be a squared e to the ax. Now I could plug in e to the ax, a e to the ax, a squared times e to the ax back into the original equations. From here, I can factor out an e to the ax. And we can see here that this equation can factor out to two binomials. So we can factor this out as a plus 5 times a minus 2. So a would be -5 and a would be equal to 2. Since the roots of the equations are real here, write this as y is equal to a times e to the -5x plus b e to the 2x. Alright, so in this next problem here, let's suppose x and y be an element in the integers, and we need to prove that if x squared times y squared minus 2y is odd, then x and y are both odd. I remember this method, and we use the method by contrapositive. Write out the proof here. Let's assume that x and y are even. Then there exists a k inside an integer, which is an integer, such that x is equal to 2k. Then x squared is y squared minus 2y. I'm just replacing k for x. 2k squared is y squared is 2y. Which is then equal to 4k y squared minus 2y. Then let me back up. Let me take out a 2 here. So 2 times 2k squared y squared minus 2y. And we can see that it is even, which is even, since 2k squared we can know that it's an integer. And similarly, if y is even, then there exists an L inside as an integer such that y is equal to 2L. Then place the 2L here. Which is then equal to 2 times x squared 2L squared minus 2L, which in this case is even. Since x squared over 2L squared minus 2L is an integer. So in this next problem here, let I be a closed and bounded in R. And let's suppose a function I to R is continuous. And we need to prove that f of I is a closed and bounded interval in R. Let me write the proof. Let's suppose by contradiction that f of I is not bounded. Then, for all n inside the natural numbers, there exists a point x of n in I such that the distance of xn is greater than n. And we know that since I is closed, and bounded, the sequence x of n has a convergent sequence, which is x of nk converging to some c, which is an I. And since f is continuous at c, then f of nk goes to f of c, so f of nk must be bounded. But this is a contradiction, right? But this contradicts. That the distance between f of nk is greater than nk and greater than k for all k inside of n. Therefore, f of I is bounded. But we also need to show that f of I is closed in this case. Let's take a sequence. Yn and f of I such that f of xn is equal to yn for all n. And since I is closed and bounded, it follows that there is a subsequence x of nk converging to some point C, and f of c is equal to the limit as k approaches infinity of f of nk, which would be equal to the limit as k goes to infinity of y of nk is equal to y. Therefore, f of c equals y, which implies y is an element in f of I. So in this next problem here, let m times d squared x over dt squared is equal to negative k of x minus c times dx dt plus b times cosine of w0 t. And we need to find c is equal to 0 and determine the particular and general solution for this equation. So let me find c is equal to 0. So let me plug in c for 0. So this is the formula of this equation when c is equal to 0. Now, let's determine the particular solution for this. Let w0 not equal to square root of k over m. So kp would be b divided by k minus mw0 squared times cosine of w0t, and let w0 be equal to k over m, m times w0 plus sine of w0t. This is the particular solution. And now we need to find the general solution for this problem. So let's say x is equal to xp plus c1 cosine of w plus c2 sine of wt where w is equal to square root of k over m. This would be our general solution. So in this next problem here, if G is a group and H is a subgroup of index 2 in G, prove that H is a normal subgroup of G. So write out the proof here. So let's suppose H and AH be the left cosets of H in G, and H and HB be right cosines of H in G. Since there are only two cosets, A of H is equal to G over H, and HB is equal to G slash H. Then we have AH is equal to HB. And now we need to show that H is a normal in G. And we want to show it that x of H is equal to H of X for all x inside G. So let X be an element in G. If X is an element of H, then X of H is equal to H. That is if X is an element in G slash H is equal to B, then there exists an H1 and H2 inside G for an H such that X is equal to A H1 equal to H2B. Then X of H is equal to A of H1H is equal to H is equal to HB is equal to H2B, which is equal to H of X. That is X of H is equal to H of X for all x inside G. This is an example of an abstract algebra problem that I learned. Alright, so in this next problem here, we're trying to solve the integral of sine of z over z squared plus 9 using the Cauchy integral formula. So let me rewrite the Cauchy integral formula. F of 0 equal to 1 over 2 pi I over the integral of f of z minus z0 dz equal to 2 pi I f of z0. And let me rewrite the equation. This z squared plus 9 can be factored out, breaking down into z plus 3i times z minus 3i dz. And based on the formula here, z minus z0 would be this one, z minus 3i, and we would have the sine of z over z plus 3i as f of z. So let me rewrite that. This would be f of z, and the bottom would be z minus 3i, which would be z minus vi. From here, we could, from the formula here, we know that 2 pi I times f of z0, and we could just replace the 0 with 3i. So 2 pi I over sine of 3i over 3i plus 3i. And this would be, simplifying from here, side. And we can see that the i's will cancel. And this would be written as pi over 3 sine of 3i. And now we could write this in hyperbolic function. So this would be pi over 3, and sine of 3i would be e to the I, 3i, minus e to the negative I, 3i, over 2. And then from here we can simplify here. This would be a negative 3 here. This would be a positive 3 or 2. And now this could be written as pi over 3 sine of h in the hyperbolic form. So this is an example of a complex analysis problem that I learned. So in this next problem here, we're trying to find the solution to the wave equation utt minus 4uxx is equal to 0 with initial conditions of ux0 is equal to sine of x, of x0 is equal to 10. So to start off, let's solve the initial value problem. Let me do this. Given that, so those are our three equations right there. And now let me write this as uxt is equal to 1/2 plus u of x minus 2t of 0 take 1/4 of the integral of x minus 2t and x plus 2t of ut, and we would have s of 0, yes. Now let's do x, uxt is equal to 1/2 over sine x plus 2t plus sine of x minus 2t plus 1/4 over the integral of x minus 2t x plus 2t of 10 ds. Half of sine of x plus 2t plus sine of x minus 2t plus 1/4 4t times 10. Then simplify from here, ut is equal to 1/2 over sine of x plus 2t plus sine of x minus 2t plus 10t. And now we could check. So let ut is equal to 1/2 of negative squared, negative 2 squared, sine x plus 2t minus sine of x minus 2t this would be UTT is equal to, let's see, 4 over 2 of negative sine x plus 2, x plus t minus sine of x minus t is equal to 4u xx. Now u of x0 would be equal to 1/2 times sine x plus 0 plus sine of x minus 0 plus 0 is equal to 1/2 times 2 sine of x equals sine of x. And we have u of t of x and t is equal to 1/2 time over 2 cosine of x plus 2t minus 2 cosine of x minus 2t plus 10. And then this would be ut of x0 will be equal to 1/2 2 cosine of x minus 2 cosine of x plus 10 would be equal to 10. And therefore, we solve the initial value properties from these equations. Alright, so in this problem here, we're given that the joint density function of x and y is given by f of xy is equal to 2 times x plus 2y over 3 if x is between 0 and 1, and if y is between 0 and 1. So we're trying to find the conditional density of x, given that y is equal to y. So we need to use the marginal density function. So we can write this as f of xy is equal to integral of 0 to 1 f of xy dx equal to the integral of 1, 0 to x plus 2y 3 dx. So we could write this as integral of 2x plus 2y over 3 dx is equal to integral of, rewrite this as 2 over 3x plus 4y y dx. This would be, the integral of 2 over 3x would be 1 over 3 x squared plus 4 over 3 xy. Now I can plug it in for f of 1, which would be 1/3 and for f of 0, this would be 0 here, and this would be, if we subtract those two, we would get 1 plus 4y over 3. Therefore, the conditional density of x, given that y is equal to y, can be written as f of xy is equal to fy over y. So this would be 2 over 3 x plus 2y over 1 plus 4y over 3, which is equal to 2x plus 2y over 1 plus 4y. So in this final problem here, let x1 to x2 all the way to xn be a random sample from a uniform 0 to data where data is unknown. And we need to find the expected value and variance of data hat. So let me find the expected value first of data hat. E to the data hat is equal to 2 times E, the expected value of x bar, and E to the data hat is equal to 2 times 1 over n times E to the x1 x1 plus x2 plus all the way to xn. You see that E, expected value of data hat, is equal to 2 over n times n over data over 2. And now we can see that the n's cancel out and the 2's cancel out. So now we have e to the data hat is equal to data. And this is our expected value of data hat. And now let's find the variance of data hat. The variance of data hat is equal to 4 times variance of x bar. So the variance of x bar is equal to 4 times 1 over n squared. Now we have the variance of x1 plus x2 plus all the way to xn. Now this variance of data hat is equal to 4n squared times n over data squared over 12. And the variance of data hat would be equal to data squared over 3n. So this is the variance of data hat. Alright guys, thank you so much for watching this video. That was me showing every math course that I took in college. So hope you enjoyed this video. Please subscribe and I'll see you in the next video.